So, today what I am going to do is I will describe in in a bit details about these two papers. I mean, today I will discuss the first one, this Cahill and Glauber. I do not think I can discuss the entire paper, and next class I will try to discuss the second one. Now, why is it so? So, one thing is of course for technical reasons. So, these two papers are very helpful in order to apply the phase space distribution functions and their properties to study quantum information, that is first thing. Secondly, if you want to connect different phase space distribution functions like p distribution, q distribution, symmetric, I mean the Wigner distribution, this connection is established through their formalism. Okay. So, you can connect these distribution functions in in a concrete way. And third one is that although these S parameterized ordering is generally of not much use in applications, but as I said, this connection, to establish the connection among these different well known distribution functions, this S parameterized distribution function is quite useful. The other thing is that for example, I talked about this expressing a bounded operator in terms of a displacement operator, which is a known process. Question is, which is a kind of mathematical question, is that when can a bounded operator have such an expression which is kind of convergent. If I write it in terms of integral, infinite integral or sum, then the question is whether it is convergent or not, otherwise I cannot use it. Okay. So, these are the issues which are discussed in these papers, these two papers. Okay. So, this is why I thought that maybe it is a good idea to go through those papers, not in much details, because that you will have to do, but at least the basic things that are required. Okay. So, this is what I am going to do now. Okay. So, so again I would suggest that you should go through these papers in details. You should try to reproduce their calculations also, because that is very very useful. Okay. Okay, good. So, so couple of things which I will require here is, so I often use this notion of two dimensional delta function, right. Okay. So, what actually it means? So, this Cahill and Glauber, maybe I will write them. Yeah, I will just write them, maybe for completeness. This is ordered expansions in boson amplitude operators. This is by K. E. Cahill. I mean, he was a PhD student of Roy Glauber, okay, and Roy J. Glauber. This is in Physical Review, not Physical Review A, because at that time there is no Physical Review A, volume 177 and page number 1857. and then what is that 1969. The second paper which I will discuss, maybe not today, later, it is called density operators in and quasi probability distributions. Again by Cahill and Glauber. Physical review. This is 177, same volume, page 1882, 1969. Okay. Yes. So often we need to use, and this I have used also earlier, this two dimensional delta function, and this is by definition, this is delta, that one dimensional delta function, a real part of alpha times delta imaginary part of alpha. Okay. So, by definition this is the two dimensional complex delta function. Okay. Right. So, if you now take the expression for delta function as a Fourier transform of function constant function 1, right, then you know that delta of x, this is a real parameter, delta of y times delta of y, this is 1 by 2 pi square minus infinity to plus infinity, minus infinity to plus infinity, this is dx dy e to the power iota x k plus y k prime, this is k and k prime, right. This is the product of these delta functions, this is real, these two are real variables, right. So, now if you take this as definition of product of two delta functions, then you can figure out that this is nothing but, look at here, this is the usual Fourier transform 1 upon 2 pi and the Fourier transform of the constant function 1, right. Now, if you do this thing, if you apply this definition, this property here, what you will get is the following. This is 1 upon pi square beta d square beta. So, this is the complex integral. Then this is the complex Fourier transform of the constant function 1. So, alpha beta star minus alpha star beta. Okay. So, two dimensional delta function. So, basically point is that if you use this definition here, what you will get is this one. Okay. So, this is the basically two dimensional delta function. Okay. So, the interesting thing is usually when we do real Fourier transform, I will take in the Fourier transform 1 upon 2 pi in one dimensional cases. Inverse Fourier transform I will not take this 1 upon 2 pi, but in this notation you will see that inverse Fourier transform and Fourier transform they behave symmetrically. Okay. Right. So, in other words, if you take, let us say I consider the Fourier transform of this function 1 upon pi beta belonging to C d square beta. So, I take the Fourier transform, complex Fourier transform, which is alpha beta star minus alpha star beta. So, this is the complex Fourier transform of this function g of beta. Okay. So, I consider the complex Fourier transform of this function, which I am calling at f of alpha. Now, if I look at the inverse Fourier transform, that means I want to figure out g of beta as integral in terms of f of alpha, what you will see is the following. This is 1 upon pi alpha belonging to c d square alpha, this is exponential of minus alpha beta star minus alpha star beta, then f of alpha. Okay. So, this is what we do in the usual case. Only thing is, look at this factor, these are same.
So, it's 1 over pi here, but 1 over pi square there.
That is the definition of delta function, two dimensional delta function, but for generic function this is what you will get. So, it behaves symmetrically for Fourier transform and its inversion. Only change is, you see, this thing, you will have to take the negative sign here. Okay. So, in other words, if f alpha is the Fourier transform, complex Fourier transform of g beta, then g beta is complex Fourier transform of f alpha. Okay. Is that clear? Okay, good. So, now you know some of the properties of the Fourier transformation, which we will require later, but I will just mention them, it's a. So, let us say that g beta or say g 1 beta, this is the Fourier transform or complex Fourier transform of f 1 alpha, right, and let us say g 2 beta, again complex Fourier transform of f 2 alpha, right. Then this is the usual inner product kind of thing which we do is d square alpha f 1 alpha bar, so complex conjugate of f 2 alpha, this should be equal to beta belonging to c d square beta g 1 beta bar g 2 beta. Okay. So, this is usual one which we see in the so there will be some some factors here for real Fourier transform, but here you see this is the relation that you will have. Okay. I mean just you take the definition of the Fourier transform, you will get this. Okay, good. And so, when does a Fourier transform exist of a function? If it is square integrable, right, if it is square integrable. So, if f of alpha is square integrable, then you define its norm of this thing as 1 upon pi alpha belonging to c d square alpha mod of f alpha square to the power half. So, because this is square integrable, this integral exists and it is finite. Okay. And therefore, it satisfies all these properties of norms. So, in other words 1 upon pi alpha belonging to c d square alpha f of alpha g of alpha, both are square integrable function. So, this you can show that this is less than equal to norm of f times norm of g, right. Okay. just you use the Schwarz inequality. Anyway, so so this is all known. I mean, just I am talking about it for the case of for complex Fourier transform, right. Now, this we have discussed that if I take an operator f which is a bounded operator means that norm of f which is, so square of this is trace of, so this is the Hilbert-Smith norm. Okay. So, this is finite. Then I say that f is bounded. Okay. So, this we have seen that this is 1 upon pi alpha belonging to C d square alpha trace of f d alpha then d of minus alpha, right. Did I prove this? I think so, right. Okay. So, you can write it as a linear combination of the displacement operator for bounded operators. Okay. So, this is again a function of alpha, this is what is called as weight function. Okay. Okay, good. So, this we have proved that if this is a bounded operator, then you will have such a representation. Okay. Right. Okay. So, what we need to prove is the opposite one, in the sense that if you have a bounded operator, okay, so the converse. So, this I said that if f is a bounded operator, then it will have such an expression, okay, and how to prove that okay. So, this is for you to verify, I do not know whether I have told you to do that, is that this norm of f is equal to, so let us define this f of alpha, the weight function. So, this is my f of alpha, okay, this weight function. So, you can prove that this norm, and this is norm of the operator which is this, and this is the norm of the function which is that one. So, you can prove that for bounded operators these two are same. Okay. So, this I am not going to prove, you can prove it. Okay, good. So, converse is that I mean, for a bounded operator if I mean whether f is equal to alpha belonging to C d square alpha f alpha d of minus alpha with f alpha is equal to trace of f d alpha, f is unique and square integrable. Okay. So, and of course, this is also true, and so basically this is both way, this is true, that if I take a bounded function, then it will have such an expression, okay, where f alpha is given by this quantity which is the weight function, f alpha is square integrable, and this norm condition exist. Okay. Right. Now, so this is, this is simple, I do not want to prove that this is, this you can. So, this now the one important thing is that I am never demanding that the magnitude of this function is always bounded, that I am never demanding, okay? Because even if this is unbounded at some point alpha, still this integral can converge, right. Okay. So, boundedness of operator capital F does not guarantee pointwise boundedness of this function, weight function. Neither it would guarantee continuity of this function, because even if this is not continuous, still this can be finite. So, bounded operator does not mean that the corresponding weight function is bounded as well as continuous. Okay. But we will see that there are specific types of bounded operators which are called trace class operators, for which both these conditions hold good for the weight function. So,
both the value and the
yes. So, if f is trace class, then the weight function f alpha is bounded and continuous. Trace class operators means that, so trace class operators of course necessarily has to be bounded, but it is more than that. So, a bounded operator, you do not have to mention that, basically I call it as f of 2, this is another norm. So, this is defined as trace of square root of f dagger f. Okay. So, some people call it as trace norm. Trace norm. So, f is a trace class operator. This means that f 2 is finite. Okay.
so F2 is different from F double bar, but
Yes.
without 2.
Yes. Why? Because this is what is called as Hilbert-Smith norm. So, this is square root of trace of f dagger f. Okay. So, bounded means this is finite, Okay. So, if I take a trace class operator, is it a bounded operator?
Yes, of course, from that definition.
Which definition?
If f is trace class, then f alpha is bounded and continuous.
No, 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 no. I am talking about operators. So, my point is that F2 is finite, that is F is trace class operator. Does it mean that this is finite?
Yeah, because square root of a finite number is finite. Oh no, sorry.
These two are different, you know. This is trace of square root of this. This is square root of trace of this.
It is square. Then we have
So, definitely these are positive operators, right? So, I can have a spectral decomposition and all that.
they will be greater than.
Which one is greater?
If you square both of them,
Uh-huh.
then trace class value will be greater than this value. So they have to be finite. The other one has to be less.
So, what does it mean? Can I write this thing? Is that correct statement?
Yes, I think so.
It has to be. Huh? So, every trace class operator is a finite operator. I mean not finite, bounded. Every trace class operator is a bounded operator. But the opposite is not true. There can be bounded operators which are not trace class. Okay. Yes. So, can you think of some example where it is bounded operator but not trace class? So, that means this is finite, but this is not. Okay, good. What about f is equal to d alpha?
It's a delta function.
Maybe this is not a good example. Maybe not a good example. Yes. So, basically what I want is example of a bounded operator which is not trace class.
So any operator which is divergent would be, but still bounded
Divergent but still bounded means
at
what?
some values. So this delta alpha will be, d alpha will be the case, because I think d alpha has a delta function.
No, but d alpha is not trace class.
Yeah, that's the thing. That's what we want, right?
But d alpha is also not a bounded operator.
It's not bounded.
No.
If you take trace of a infinite identity, right?
Yeah, because this is if you take f is equal to d alpha, then this is square root of trace of d alpha dagger d alpha, which is identity, and this is infinity. Okay. So, d alpha is not a good example. So, basically
Some kind of a square root of identity where half the eigenvalues are -1 and half are +1.
maybe that kind of thing. So, basically this tells you that this is finite, but this is infinite. Okay.
The position operator has eigenvalues negative and positive also.
Position operator will not work. This is not work. Yeah. Anyway, we'll have to figure out basically what sort of operators are trace class and bounded operators. Okay. Let's see. How do
If you draw any function f alpha,
yes.
will it correspond to, if it's at function level, if it is square integrable, then will it correspond to a bounded operator, right?
Exactly.
So we can take example from there. We can take a non-continuous but square integrable function
That is bounded.
that is bounded.
Yes.
So just put a
Yeah, from there we can in principle calculate this thing. So, basically what you need to have is how to say that
taking trace over f dagger f is like we have some numbers like bra m f dagger f ket m, right? Something like that. So that is
maybe that is it's a kind of thing. So, let me put it, let me take any this is may not be very physically motivated example. So, let us take f is equal to sum over, let us say n is equal to 1 to infinity, I am not taking 0, 1 upon n n n. So, these are the Fock states, okay, right. So, this is an operator. Is it a bounded operator?
yes, because sum will be
Yes. So, what is this?
1 by n square sum over.
This is convergent, right? This is finite.
So 1 by n will not converge.
Yeah, and what about f of 2 here?
So it's 1 by n summation.
No, this is trace of square root of this, right? So, therefore, this is again 1 upon n n n, right? And this is of course not convergent, right? This is basically infinity. I mean, this is may not be very well motivated example, but this is the kind of thing. Okay. Okay, good. Yes. So, basically point is that if f is bounded operator, then you can figure out a square integrable weight function, which is basically this f of alpha is this, and to express f in this form, right, and where all these conditions will be satisfied. There is another norm which we also use, which is called F1 norm. So, which is like least upper bound over all psi so that they are normalized one of this psi f dagger f psi. So, this you can say loosely that this is basically the largest eigenvalue of f dagger f, okay, right. Sorry,
Psi is what?
psi is a state which is normalized. So, you take the expectation value of f dagger f with respect to psi,
It is any state.
any state which is normalized.
LUT
This is called least upper bound, you know. What is that? Huh?
I mean, some values can be greater than some values.
I mean, this is, well, for certain functions this will be maximum, you know, maximum eigenvalue. Yeah. No, because we are dealing with infinite dimensional systems, so one should be careful about maximum and the least upper bound, greatest lower bound, all these things are there.
So
But
this will be always there in psi which is diagonal in f dagger.
no,
It can be maximized in non-diagonal basis.
no, I am saying that loosely speaking, this is, you can say, like this is the maximum eigenvalue of f dagger f, loosely speaking, when maximum exists, otherwise not.
So what is that thing LUE, least upper bound?
Now, how does it define least upper bound? So,
Is it min max or is it mathematically different from minimum of
yeah,
maximum?
no, it is not max. You know, the point is, you calculate this quantity, okay, right, for all psi such that they are normalized, okay. So, you calculate this quantity, right, and then you know, so you basically you consider the set. So, set of all those values for given f dagger f or given f, all those values, okay. So, this will be generally, this will be a non-negative number, right.
Yes.
Now, this set you try to figure out what is the maximum of this set, because this is a set of numbers, non-negative numbers. What is the maximum of this? Okay. So, now this maximum may be achieved at a certain psi, right, okay, or you may figure out that no such psi exists for which this maximum is achieved.
Maximum must always be there.
Maximum will be there if this set is compact set, otherwise it may not be.
It might be infinite.
No.
Oh, you are
That
saying
it will approach
Depends on the set. If the set is open, for example, 0, 7 is your set.
Yes.
Open-ended set. What is that open? What is the
So
maximum?
if it's open at 1 and 1 is
so. That in that case, what by definition, what is this f1?
By definition, yes. So, this is what is called as least upper bound.
So I mean, I understand the upper bound part. If there is a maximum, that is this f1.
Yes.
Uh,
If maximum does not exist,
then
then
so
it is the where it asymptotically approaches kind of.
yes. So, maximum does not exist means that no such psi exists for which this quote unquote maximum value can be achieved here. Okay. But this is still an upper bound. And how good this upper bound is? You choose any other upper bound, that any other upper bound will be greater than or equal to this least upper bound.
oh, so in case there is no maximum, then you take the limit of where it's
Exactly. Yeah, I mean this is, I am sure you read it in calculus, you know, this is what. Okay, so this is the norm, right? and there is this now can you say something about the relations among these three now? This we have seen. What can I say about this F1?
All of them are square rooted in the end. This one is just bare. So, I mean, there might not be any connection.
Are you sure? Look at this. So, in principle, this is square root of sum of all the eigenvalues of f dagger f, right?
So, we'll have to square this and then complete.
Is this the definition of f?
It should be a square root, you are saying?
Maybe, yes.
Maybe then only you can compare. Yeah, right.
If it's square root, then this should be the least of all.
It's a definition, right? So
Which is the least of this? I think it should be a square root, otherwise it does not make sense. Yes, otherwise you cannot compare. Yeah.
And then it will be smallest of f2 and
Yes. So, this I think then can I say that this is less than equal to, is that a correct statement?
I think so.
Yes. Okay. So, this is the relation. Yeah, the square root should be there. Okay. Okay, good. So, we will use this relation in future. Okay. So, now there is a some interesting thing which you can observe. So, number one is, so far we have seen that arbitrary operator can be written as a linear superposition of displacement operators, provided that operator is bounded, right, that we have seen. So, in principle, if I take this operator f is equal to this one. So, this is a coherent state, this is another coherent state. Is this a bounded operator? What is the definition of bounded operator? This is your definition.
So, it's not bounded because if you take beta is equal to alpha, then so what is this thing?
This is outer product of the these alpha and beta coherent states. Okay.
So, we can take beta is equal to alpha. Right?
Fine. It is not bounded. Why?
Because alpha was not bounded, right?
Alpha is a coherent state.
Okay.
Look at here. What will be norm of this operator?
1.
1. So, therefore, this is bounded, isn't it?
But don't we have a delta?
Where is delta?
When you take Ramka, it will be just inner product of. Oh, yes, yes.
Okay. So, this is a bounded operator. So, f is equal to 1. So, therefore, this is bounded operator. What about f2? Is it a trace class operator?
Yes, that's also 1.
Yes, this is also 1.
Yeah, everything.
So, therefore, this is both bounded as well as trace class operator. In fact, trace class means it is bounded and trace class. What about f1? f1 is 1? Yes, yes, it is 1, right. So, I can have that representation. Okay. So, I can write therefore, alpha beta is equal to 1 upon pi gamma belonging to C d square gamma trace of alpha beta times d of gamma, then d of minus gamma, right. This is my weight function and this is a convergent integral, it has to be. And so, this is 1 upon pi gamma belonging to C d square gamma, this is beta d gamma alpha d of minus gamma. Okay. Is that clear? So, here I have of course assumed that the expression that I mentioned earlier, that if it is a bounded operator, then you can have this kind of expression. So, therefore, this is a valid one, right. Okay. One more thing, in fact you can prove it also independently of that property, you can prove it directly. Okay. So, this is like forget about the result that I mentioned, like f as a superposition of the displacement operator, forget about that, but you can prove this thing independently of that. Okay. Now, why this is important? Because if you know that this outer product has this expression, then you know that any linear operator can be written as a linear superposition of this outer product, and therefore, any linear operator if it is bounded, it can also have such an expression. Okay. So, one can prove this thing independently also. But what is more important, I would say, is that if you take now trace of this, okay. So, because I want to have an operator form representation, so this is a scalar and therefore, I multiply by identity. So, this you can write as 1 upon pi gamma belonging to C d square gamma d of gamma alpha beta d of minus gamma. See, this is so nice. You have this identity times this scalar, it is basically product of these three operators. Okay. Yeah. So, yeah, maybe so, I will try to prove this thing. Okay. Now, one may say that what if I take trace over here? So, let us take trace over here, will I get that? So, trace over these. So, if I take trace, so after taking trace, so this will be beta alpha, right, and what about this? This is 1 upon, I am not bothered about this identity, that is okay. So, this is 1 upon pi gamma belonging to C d square gamma, this is beta d gamma alpha. Now, trace of this thing, trace of this thing I have done it earlier. If you do not remember, trace of d of alpha is equal to pi times delta 2 of alpha. Okay. So, this you can verify, but this is what I am going to use. So, here it should be pi will go away, delta 2 of alpha, right. Okay. But then how to get this one? This is a scalar, and this is an operator. So, straightforwardly you cannot get this one from here. So, what we can do is the following. This trick we adopted earlier also. So, we are going to do it now. I mean, in fact, the same trick you can apply to prove this also. So, basically you choose two arbitrary coherent state eta and epsilon, two arbitrary coherent state, and show that if I take this matrix element of the operator, what is that operator? Yes. Yeah. So, if you take this operator, matrix element of this, okay. So, this is, you know, what is this? This is eta, alpha, beta, epsilon, okay. And then you take the definition of this inner product and this inner product, the usual definition. So, what you will get is the following. So, you will get it like this: beta alpha times eta epsilon, okay, times exponential of beta minus eta star epsilon minus alpha. Okay. So, this is the expression that you will get. Okay. And if you take this one again eta, then this whatever is on the right hand side 1 upon pi gamma belonging to C d square gamma, this is beta d of gamma alpha, then d of minus gamma epsilon. What you will see? You will get the same result, exactly same result. Okay. So, this means that as operators these two are same, right, because you are taking matrix element with respect to these bases, coherent state bases, and because these two are same. So, therefore, you can say that these two operators are same. And not only that, you can say from here that because you know this is the relation, what is that, yeah, yeah. So, what you have seen is that this quantity is same as this quantity, right? Yes.
I mean, something is wrong in writing. The inner product.
Yes.
The last line. It will. There was d gamma alpha beta d minus gamma, something like that was.
Yes. Yes. That is what I have written, right?
So you are taking inner product of some. This is just a number, right? Inside.
This is a number, but this is operator.
Oh.
Okay. Yeah. So, using this equality, this one and this one, what you can prove now is that eta alpha times identity. Okay. So, basically you can forget about that. Why I am asking you to forget about that? Because you will have this matrix element basically. So, what is that matrix element? Basically this one and this one, okay, these two matrix element, right, whatever is there. So, this will come here, right, this eta. So, what you will see is that this is 1 upon pi gamma belonging to C d square gamma d of gamma alpha eta d of minus gamma. Okay. And this is exactly what you wanted to prove here. Where is that? This one. So, you replace eta by beta, this is what you will get, right. Is that clear? Because these two are same, you look at this matrix element corresponding to these bra beta and ket eta. So, which is like this one and this one. So, then whatever is there inside, those will be same. Okay. Right. Okay, good. So, this is fine and this is quite useful. So, you see that this is, so first of all the result that I mentioned earlier, that arbitrary finite bounded operator can be written in terms of this integral of weight function and the displacement operator. This holds good, of course, this is a bounded operator, this should hold good, but irrespective of that result you can prove it. And this is, this is a kind of basis element of operator basis, which you can also express in terms of these this displacement operator. And not only that, this inner product, this basically this identity, it has this kind of operator expansion. Okay, right? Okay, good. Any arbitrary alpha beta, yes. Yes. And this is the technique that we will use every now and then, that we express the matrix element and show that between two operators the matrix elements are same for arbitrary coherent state basis. Therefore, the two operators are also same. Okay. What about, so if f and g are bounded operators, then trace of f g, what will be this? So, I write trace of, for f I write this 1 upon pi alpha belonging to C d square alpha, trace of f d of alpha, then d of minus alpha and times this g, right. And now I can take this trace inside. So, basically what will happen is trace of g d of minus alpha. Okay. So, if you now take this one, so you can use Schwarz inequality to prove that this is basically less than or equal to norm of f times norm of g. What is norm of f? Norm of f is norm of this weight function, and norm of g is norm of this weight function. Okay, here minus alpha, but that does not matter. Okay. So, for bounded functions, bounded operators, this is what you will get to see. Okay. One more thing which is also very useful is that if you consider, so far we are considering the coherent state basis. If you consider an orthonormal basis, which may be your number state basis, maybe not. So, let us say this is an orthonormal basis ONB. So, A will run from, I mean basically this number of A's will be infinite for my system. So, this is an orthonormal basis. Now, if I look at this function. So, let me call it as f a b alpha, which is defined as a d alpha b. So, for given two basis elements, this is my function. Okay. So, you can prove that these functions is, so this class of this f a b alpha over all a b, this forms a complete orthonormal basis of functions. Okay. So, this is complete ONB of functions. So, how do you prove that? First of all, they are orthogonal. I mean, if you take alpha bar, let us say f c d alpha 1 upon pi alpha belonging to c d square alpha. Okay. So, this will be something like delta a c delta b d, something like that. Okay. So, this is kind of orthogonality, and then you can prove that it is any function, well behaved function can be written as a linear superposition of this thing. Okay. So, anyway, so I am skipping most of the things because I cannot do all of them together. Okay. So, and this property will be useful later that they form. So, basically you can say that this will form a functional, I mean a basis for functions, okay, just like what we do for Fourier basis. Okay. So, it is like that. Okay. So, when we choose these number basis, okay, Fock state basis, this is my Fock space. So, you can say these are the energy eigenstates, etc. Then these functions, so now you will have f m n alpha, which is like m d alpha n, right. This is my definition. So, the matrix element of displacement operators with respect to the Fock states. Okay. So, this is actually well known. This you can write in terms of these associated Laguerre polynomials. Okay. So, anyway, I am not going to derive all those things. This you have done, back in MSc classes. This is what you have done. This is associated Laguerre polynomial. So, this multiply m minus n e to the power minus alpha square by 2 into L n m minus n mod alpha square. So, this is the associated Laguerre polynomial. In mod alpha square. Okay. And this we know that they form a basis, orthonormal basis. Okay. Right. Okay, good. So, this is actually enough for this. So, one important aspect is that, so basically what we have seen is that f is a bounded operator, right. So, this means that f is connected with this weight function, which is trace of f d alpha. Okay. And we have seen that there is a one-to-one correspondence between the class of all bounded operators and the class of all the square integrable functions, in the sense that given any bounded operator you can figure out a square integrable function, and given any square integrable function you can figure out a bounded operator, okay, which are related through this relation that f is equal to 1 upon pi alpha belonging to C d square alpha f alpha d of minus alpha. So, this we have seen, right. Okay. So, if you look at here the expression for f, you see that this is equal to 1 upon pi alpha belonging to C d square alpha trace of f d alpha, and then exponential of minus alpha a dagger plus alpha star a, because of this thing d of minus alpha, right. So, this is you see something like so I can make, for example, maybe I will correspond it to some function g of alpha, and this I correspond it to this Fourier component exponential of beta alpha star minus beta star alpha, in the sense that you replace this a by beta, a dagger by beta star. Okay. So, then you will get this Fourier component which is a scalar, and this is something like there is a correspondence with this weight function. Okay. So, in other words, given this expression you have a kind of correspondence of this operator with the following expression 1 upon pi alpha belonging to C d square alpha, you can call it g of alpha, then exponential of beta alpha star minus beta star alpha. Okay. So, this is something like operator and function correspondence, and this is what we have been using, and this is what we will also use later. Okay. So, this I told you at the beginning that when you take normal ordering or anti-normal ordering or symmetric ordering, you will have to replace, to get the statistical behavior, you will have to replace the operators by the scalar quantities, this alpha, alpha star, etc. So, this is what you talk about the correspondence. Okay. Okay. So, basically you will have a and a dagger which will correspond to alpha and alpha star. Okay. Fine. So far so good. We talked about the bounded operator and square integrable function and their connection. Okay. What about unbounded operators? Okay. Like unitary operator, displacement operator, they are unbounded operators. Can you have such a correspondence? Okay. In fact, if f is an unbounded operator, generically even if you write it in this form, I mean by force or something you write it, this is your weight function, generically this is not square integrable. but of course, there are exceptions where you can have unbounded operators, but still this can be square integral. Okay. In fact, what can happen is that for unbounded operators, for specific values of alpha, this is unbounded or singular, but that does not mean that if I do this integral, this is not finite, this can be finite, right. So, those things can happen. Okay, good. So, let us look at it more carefully. So, let us take this example, f is equal to d alpha. This you know, this is unbounded operator, but it is what about your, is it a trace class operator? Is it unbounded operator? Okay, let me see. What is f? 1, right? This is 1. So, this is not unbounded operator, isn't it?
D0 is identity.
What is the definition of these? Square root of trace of f dagger f, right? Oh, it is, this is the definition. So, this is unbounded, sorry, this is unbounded, yes. So, this is unbounded, this is plus infinity. So, this is unbounded. Okay. What about f1 here? f1 means the square root of the largest eigenvalue. So, you can say least upper bound over psi.
This is bounded. This is the 1.
This is 1, right? So, this is a finite operator. So, when this is finite means we say that f is finite. This is a finite operator, okay, right. So, what is the weight function here? F of beta is equal to trace over f d beta, and which is trace over d alpha d beta, and which is trace over d alpha then d of minus beta inverse of that, and this is pi times delta 2 of alpha minus beta. Of course, this is singular, right. Okay, right. This is singular, right. But of course, you know what happens if you integrate it?
1. Okay. Identity 1.
You will get 1, yes. So, this is your 1. So, you see that this is square integrable in that sense, but of course, this is singular. So, this is what I said, I mean this may be square integrable for unbounded operator, but for specific values of beta this can be a singular. Okay, good.
If
Yes,
and also square integrable.
continuous functions are square integrable. Yes.
Yeah, then its operator will be bounded on corresponding operator.
That's what I said. Um,
It will be trace graph actually.
yes, it will. Oh, you have a lecture. 3:30. What is the time now?
20.
Oh, okay. I think 3:20. Yeah.
Are you okay 5 minutes?
5 minutes. I'll-
Okay, I hope they're open 3:30.
Yeah, sure. Okay. Oh, I don't know. Is there a from 3:30? Is there a seminar notice? Anyway, so basically, I mean, in terms of these displacement operator, if your operator is unbounded operator, in terms of displacement operator, you may not have a convergent representation. Okay, that may happen because if this function is ill-behaved, then it does not make sense. But what can happen is the following, and this is quite important. So, displacement operators is a class of operator that forms a complete basis. But you can also take this class of operators. Okay, this will also form a basis. So, what you can write is you can write in this form. This is what we have done at the very beginning. Alpha beta belonging to C, this square alpha, this square beta, alpha f beta, alpha. This you can write. Okay, no problem. I mean, of course, the issue is whether this is a convergent integral, etc. That issue will come. But this convergence is much easier to tackle with compared to the convergence of this one for unbounded operator. If f is unbounded operator, then convergence of this is much difficult to prove compared to this one. Okay. So, this is your coherent state basis representation. So, any operator of course can be written in this form. The question is whether this part is convergent or not. In fact, if you take this, then you can show that if you take this one, which is trace of f dagger f, and if you take this expression, what you will get is 1 upon pi square this square alpha, this square beta, alpha f beta square. Okay. So, you see that boundedness of the operator is directly linked with these kind of functions. Okay. And here there is no displacement operator, etc. And this is, I will tell you that this is much easier to prove. Okay. And so the integrability. So basically, if I say that this function, I mean the function alpha f beta. So let me call it as some function f of alpha star beta, maybe whatever. So if this function is square integrable, then this is bounded, and vice versa actually. Okay. So what I will do next time is I will go with details about the boundedness of these, or in other words, I will consider some unbounded operator and then look for such an integral representation of that, and later some properties. Okay. I think that will okay. So we still need to talk about these ordering, normal ordering, anti-normal ordering, symmetric ordering, and then S ordering. I will briefly do that, and then I will jump into the corresponding distribution functions, okay, and I will then link them up, okay, how to connect them, and that I think will be the end of the formalism for phase space distribution function. Then we will go to, so this is so far I am talking about single mode case, but it is easily generalizable to multi mode case, and then I will go to the notion of entanglement and all that for multi mode case, particularly a particular emphasis with the Gaussian states, okay, because those are the things which are easily manageable both theoretically as well as experimentally. So, maybe another, maybe 1 or 2 classes I will describe about this generic formal, I mean the formalism, and then I will go. Thank you.